Okay.
Okay, so we are very happy to welcome Tom Meyerovitch from the Gurion University of the Negev, and the title is a multidimensional Krieger embedding theorem. Please.
Okay, thank you. So thank you for the invitation and for the opportunity to speak. So yes, what I will discuss is a new theorem, which is a multidimensional version of Krieger theorem, and I will begin by slowly and carefully describing the setup, and then I will go into proofs and details to the extent that you're interested. Okay, so the basic setup is the following, just so definitions are clear. By topological dynamical system, I will mean a group that's acting on a compact metrizable topological space by homeomorphisms. The space will later be just a Cantor space in this talk. So two dynamical systems are conjugate, topologically conjugate or isomorphic if there is a homeomorphism between them that intertwines the actions. It is gamma equivariant. Okay, so this is what I mean by isomorphic. A subsystem of a dynamical system is a closed gamma invariant set, closed topologically gamma invariant with respect to the fixed action of gamma. Okay, so x0 comes with the induced action with the restricted action of gamma. It's gamma invariant, and we say that y embeds in x. Okay, the topological dynamical system of gamma acting on y embeds in x if it is topologically conjugate to a subsystem. Okay, so there equivalently there's a injective gamma continuous injective gamma equivariant from y to x. That's what I mean by embedding. And the questions that we'll discuss will be about conditions for embedding systems. That's the now, what kind of systems are we considering specifically? We'll talk about subshifts, so symbolic systems. So the full shift over alphabet A with the acting group gamma, the gamma full shift over alphabet A is the action of gamma on the functions from gamma to A, where A is the finite set. It's usually referred to as the alphabet or a set of spins or whatever. And the action is just by composition with gamma. Okay, so I'm not writing down the formula. When it's not commutative, then to make it a left action, you need to multiply by the inverse of gamma. Right? Okay, there are two kinds of actions you can do. It's the left regular action of gamma on A to the gamma, like the left regular representation. Now, okay, I'm not seeing faces, and this is a doom talk by reaction, so feel free. I mean, you don't have to, but just I want to make sure that if at some point something is not clear or I'm lost.
Okay, so I already have a question that you refer to. Gamma is countable?
Yes, gamma. Okay, for the purpose of this, gamma is a countable. Yes.
Okay.
So the topology here is you consider A as a discrete, finite discrete topological space, and the topology is the product topology, the topology of pointwise convergence. Okay, the analog. Okay, let's not stop. There are analogs if you have non-discrete groups, but let's leave that. So gamma is a countable group. Now, a subshift over gamma is just a subsystem of the full shift for some alphabet. Okay, so x, gamma acting on x is a subshift if it's isomorphic to a subsystem of the full shift over some alphabet. That's the quick. Okay, so or equivalently, it's a closed gamma invariant subsets of gamma to the A with the action of gamma. With the induced action of gamma, with the restricted action of gamma. Okay, so is that clear? And there are other characterizations, but this is the concrete. Now, specifically, a subject of finite type, abbreviated SFT, and I will use the abbreviation sometimes just to save space, although it's not recommended to do it too much, is a subject of the following form. You have some finite set F, you could think about as a window, and then the subset, okay, curly F of the function from F to A. This you should think about as a set of forbidden configurations, things that you do not see. And subject of finite type is a system of the following form. It's all the points x in gamma to the A, okay, all the functions from gamma to A, such that no matter how you translate them, if you restrict to F, you don't see a forbidden pattern. Okay, for any element of gamma that you apply, if you restrict to F, you don't see an element of curly F, forbidden pattern. Right? So to keep an example in mind, for instance, you could take gamma to be ZD and F to be the identity together with the unit vectors, like a standard generating set of ZD. And then the forbidden patterns would be patterns on F, okay, on this, L1 ball, right, in a discrete L1 ball that contain 2 ones or more. Okay, so in this case, this is kind of a generalization of what is in Z called the golden mean shift. Okay, the set of, in the case of Z, the simplest case, is the set of all bi-infinite sequences of 0 ones where there are no 2 ones adjacent. Okay, so in 2 dimensions, it will be arrays of zeros and ones when you don't see 2 ones next to each other, okay, in the standard KD graph. That's just an example to keep in mind. So subshifts of finite type are of this form. In general, any subshift, it's of the form, okay, you have some F, which is a subset of finite configuration, it's an infinite subset of finite union of such things, and it can, any subject can be described as those configurations where some set of forbidden patterns never occurs, but usually it's a countable set, not finite. Okay, just if you, it follows from invariance and the definition of the topology, right? The compactness. Okay, so this is the setup. Stopping again to make sure there are some questions. Okay. Now, the next main notion I will describe, this is a big notion. I will do a very kind of brief and short definition. You never heard of this before, then it will be, slightly difficult to appreciate the importance of this notion. But so first of all, I defined what are the admissible, you have a subshift X and the finite subset of the group. And I denote by L, something for language, if you want to, L F of X. These are the admissible F patterns in X, the X admissible F patterns. These are, you take a point in X, which is a function from gamma to A, you restrict it to F, you have a function from F to A, and you look at all possibilities. Okay, so this is a finite set. It's a finite subset of F to the A. This is a finite set. And now if you have an amenable group, okay, there are other definitions. Let's not say what it is for a moment. Then the topological entropy is can be defined as, okay, it's not the standard definition, but it's equivalent. It's equivalent, it's defined as taking log of the cardinality of LFX, dividing by 1 over F, where F ranges all over finite subgroup, finite subsets, sorry, of gamma, non-empty. Of course, because non-empty finite subsets of gamma, you take the infimum. So this is the simplest definition. It, supposedly doesn't require amenability or anything else, but to be well behaved and nice and to deserve the name topological entropy, this works for amenable groups. So questions about the definition? And this is
so you point out, of course, because you wrote inf, this is always well defined because you didn't claim that some
right. I mean, this is just an infimum. It's always well defined. It's just let me just say by convention. Okay, a subshift. Okay, it's a subsystem. I'm usually excluding the empty set. Okay, and h of the empty set, I just will for convention define it to be minus infinity. Just for convention. And so this is well defined. That's not the problem. The problem is properties and things like that. So if the group is amenable, then this property, it's not so difficult to check that it is invariant under topological conjugacy. And it's a very important invariant. Okay, it somehow measures the complexity of the system, how big, some measure of bigness, okay? And in the following sense, so the crucial property is that if X embeds into Y, then the topological entropy of X is less than or equal to the topological entropy of Y. It's monotone with respect to embedding. That's, okay, this already tells you it's invariant under conjugacy, of course. And here is what we'll really use about it from the definition. So it's the infimum the definition was infimum over these expressions, because you can easily get upper bounds. I mean, for any finite set, you calculate the number of patterns, take log, divide by f, you get an upper bound for the topological entropy. Here's how to get lower bounds. Okay, so not explicitly, but so a set F is called K delta invariant, where delta is a positive real number and K is a finite subset of the group. If the K boundary of F is just a delta fraction of the size of F, okay? Where the K boundary, there are various ways to define it, but it's like you can think about it as points in F, which are K near points outside of F. Or points outside F, which are K near points in F. Okay, so there are various conventions, but it would not matter for the usage. And the following basic property of topological entropy is crucial. It's basic, it's well known, it's classical. It's not I mean, to refer it, probably Ornstein Weiss, but maybe in this formulation, I mean, it definitely appears in some papers by Meyerovitch and co-authors. I'm sorry if I'm not attributing it correctly, but let's say morally, it's probably Ornstein Weiss. For every epsilon, there exists a delta. Okay, so every epsilon, if you take in K delta invariant set for sufficiently good K delta, okay, K is very big and delta is very small, then if I take the estimate of the topological entropy by F, okay, take the number of admissible F pattern X patterns, so the F patterns that are X admissible, take the log and normalize, this will be roughly an upper bound for the topological entropy. It can't be, because the topological entropy is the min inf of all of these expressions, but it will at most undershoot by epsilon. Okay, so if you have a sufficiently invariant set, this quantity is roughly the topological entropy. That's the moral. And specifically, if we think about gamma being ZD, right? Then a big box is k delta invariant for any k. You know, if you choose the box to be big enough, then it will be k delta invariant. The size of the boundary would be just the delta fraction. So the number of patterns in a big box, you know, take the log and normalize by the volume of the box, this will converge to the entropy. That's the kind of more standard formula for entropy, for topological entropy. Okay. Questions so far?
Isn't it also true that it's less or equal than hx plus epsilon?
Well, it's less than or equal to, yeah, what I could have written, I'm sorry I didn't write it, but it follows from this formula. Okay, this is the topological entropy is the infimum. So certainly it's less than or equal to just h of x without plus epsilon. This expression is smaller than h of is smaller or equal to h of x.
But wait, it's maybe I got confused. It's infimum, so it's the smallest over all f.
Yeah, so sorry, what would I want to say actually? Okay, maybe. Oh, I'm sorry. Yes. Okay, sorry. I have the wrong. The inequality is reversed. Yes, of course. What this is yeah.
Okay, of course.
Of course. Thanks, Jonathan. The inequality should say this is less than or equal to h of x plus epsilon. Okay, I'm sorry.
Okay, now we are.
Yes, here is true, but it's trivial. It's so it's bigger or equal to h of x and less than or equal to h of x plus epsilon. It overshoots, but by very little. Thanks. And of course, if you notice more typos in the presentation, it's the first time I haven't used these slides before. I just prepared them for these talks, so it's quite likely that they're more. Okay, now let me recall the statement of Krieger's embedding theorem. It's a classical theorem, or I think it's considered a classical theorem. It's from the 80s by Wolfgang Krieger. And what it does, it tells you more or less explicitly, and I'll explain why more or less, what are the subsystems of the full shift in Z, in the group Z, over alphabet A. And here's what it says. A subshift, okay, over some different alphabets, so the A could be like 0 and 1, and B could be 100 letters of alphabet or 1,000 letters. You have some subshift with a very big alphabet, and you want to know if it embeds in the full shift or some subshift of finite type over 2 letters. And this happens in 2 conditions. Either X is topologically conjugate to Y, in which case the only embedding must be onto. Okay, that's a property. You cannot properly embed a mixing. By mixing, I mean topologically mixing. Topologically mixing Z subshift of finite type inside itself. It's impossible. And so that's one option. And this is kind of a complicated question to check concretely. I give you some subshift of finite type and ask you, is it topologically conjugate to the full shift? It is not known if this is kind of decidable. There's no kind of simple way. But if it's not the case, then what must happen is that the topological entropy of X must be strictly smaller than the topological entropy of Y. Okay, because if it's equal, then it must be topologically conjugate. And the number of periodic points with this period n in X must be less than or equal to the number of periodic points with this period n in Y. Okay, the necessity of this condition is clear, because any embedding passes a periodic point of period n to a periodic point of period n. Okay, so it just induces an injection of finite set. So you have and of course there's another typo here because I defined it to be the number of, because this is correct. It's not the set of.
I think it can be useful for the listeners if you remind us topological mixing in the context of subshifts.
Yes, okay, right. Okay, that's an excellent suggestion. So a subshift is, so topological mixing in general means that for any two open sets, U and V, there exists an N0 such that, oh, sorry, in the context of group, maybe, if you apply an element of the group outside some finite set to U, then it will intersect V. It will have non-empty intersection with V. For Z subshifts of finite type, what it means, okay, the subshift is a set of sequences. It means that any two admissible patterns, there exists a distance N0 such for any N bigger than N0, it's admissible to have the first pattern at 0 and the second pattern starting at N. This is what means topological mixing. Is this satisfactory, Yonatan?
Yeah.
Okay. Now, there were many questions about and extensions and the analogies of Krieger's embedding theorem. There's Mike Boyle's lower entropy factor, which gives similar. Okay, so this gives kind of simple, necessary, and sufficient conditions. Okay, they're simple at least in the lower entropy case, and it was soon asked about similar situations where such thing can occur, and Mike Boyle proved an analogous theorem for factors and not embedding. So a condition for a subject to be a lower entropy factor of a mixing SFT. Also in terms of entropy in the periodic points, it's slightly different. The techniques are similar. And one of the questions that arose for, I'm not sure where first, but it was first tackled, or the first major result was by Lightwood in the early 2000s. How to extend Krieger's theorem from Z subshifts to more general groups. Of course, it seems the first attempt should be ZD or Z squared. And now Lightwood's work, this was, I think, basically constituted his PhD thesis, and it appeared in two relatively long articles in the TDS, 2 parts. Okay, there's something about morphisms of ZD subshifts, part 1 and part 2, and there are various results, but I will kind of recap part of the result. Then I think the main part, but it does not capture all the details. And it says the following: now you have a ZD subshift of finite type, and you're asking what can you embed with it. Now, the first thing that you realize is that, in analogy to Krieger's theorem is the target. It deals with mixing Z subshift of finite type. And on a qualitative level, mixing Z subshift of finite type somehow resembles the full shift. The proof is not much more difficult than if you did it for the full shift. For ZD subshift of finite type, this is not the case at all. ZD subshift of finite type can be very strange in various ways, and even if you impose that they'll be mixing, they get quite wild. And the conclusion, a Krieger-like theorem-like conclusion, is simply not true in this generality. So you need to impose stronger conditions. I will say an example in a moment. And then Lightwood defines some condition. It's called square mixing. I will not define it precisely because I will not use it, but roughly, okay, if mixing for a ZD subshift, it means that any two configurations, if you place them far apart, they can be put together roughly. but how far apart depends on the two configurations, and you know, the distance grows as the configurations grow, and the support of the configurations grow. Okay, in principle. So I mean, by support of the configurations are like, you know, function from a finite subset, right? So the mixing is not uniform, right? For even in the topological definition, you have two open sets U and V, and you say that, you know, if you translate one by sufficiently far, then it intersects the other. How far depends on the sets U and V. So this mixing takes some square mixing takes some control of it. It says that if you have two configurations whose supports are squares, then there's a uniform distance not depending on the sizes of the squares that you can put them together.
Right.
And there's an extra condition: they must have a fixed point, which relates to some. So in 2 dimensions, this condition can somehow be removed, but in Z3 and up, it's related to some very annoying open problem. So you have subshift Y that satisfy this. For example, the full shift, it's interesting enough. Y equals 80. And you want to embed in it X. And now you know something about this X. So in Krieger's theorem, there were conditions about periodic points. And the conditions were the necessary ones. They turned out to be sufficient, that they're not more than, for every period, the number of periodic points of period n are not more than Y. So here you say, okay, forget about, Lightwood says, okay, at first step, let's forget about it at all. Assume that every point in X is free. The orbit has no periodicity at all. So it's aperiodic. That's what I mean by aperiodic. In that case, the only restriction is entropy. The entropy of X must be strong, strictly smaller than the entropy of Y. It turns out that if it's equal, it must be conjugate, and Y, square mixing, it has a fixed point, so it cannot be Y itself. Y, we assume it has a fixed point. X is aperiodic. It does not have fixed points in particular. And you can embed. This is the here. So it takes care. It's a you know, it's like Krieger's theorem with two differences. Okay, the class of subshifts considered is more restricted. This is necessary somehow. It's, I mean, it's not sure that this condition is optimal, but you cannot do with the same conditions as Krieger. And getting rid of periodic points at all. And this is kind of a big simplification of this. It's a very simplifying assumption. It's an important result. It leaves, it's completely non-trivial, and there are many strange aperiodic subshifts that give you a lot of information. But the proof of Krieger's theorem, which is relatively short, the beauty of it, or the ingenious part, is how it combines the periodic points and the non-periodic points. That's kind of the beauty of the proof. And this one eliminates this problem. So the question that remained was, okay, one of the questions that remained, the central one in this, is how to get rid of this aperiodicity assumption. And it's mentioned in Lightwood's work already. It says, okay, this is an important step in explaining it how, but it's also an initial step toward the goal of doing the, you know, complete Krieger's theorem. And this is what I undertook. And here is the result that I have. So the result is the following. I will explain it carefully. We need explanation. It says now, let Y, this is my target. Okay, so in Krieger's case, it was mixing Z SFT. In Lightwood's case, it was square mixing, the stronger assumption, Z D SFT. And here I have an even slightly stronger assumption. And it somehow need, well, I don't have a proof that it's needed completely, but it's very likely that this conditions of the type that Lightwood used are not enough for various reasons. I mean, let's put it this way. I don't have a proof that they're not enough, but at least if they're enough, then you could probably overcome, you know, this annoying open question that I'm not going into details about.
Could you say something, even in the context of Krieger's theorem, about the assumption of shift of finite type?
Right. Okay. Excellent question. So even in Krieger's theorem, okay, let's go back. Sorry. Yes. So it's certainly necessary to assume something. Okay, it's not y cannot be just a mixing subshift or something like something. It's not true. It's not optimal in this sense. For example, Mike Boyle, in the same paper where he proved the lower entropy theorem, he gave some necessary conditions for mixing suffix shifts, so subshifts that are factors of subshifts of finite type, to satisfy the conclusion of Krieger's Krieger's theorem-like construction. So there are extensions, there are partial extensions to suffix shifts, mixing suffix shift, not complete. There's a very recent paper of Sophie McDonald, who is a PhD student at UBC, jointly with Brian Marcus and myself, who have a result about Krieger-like embedding result for suffix shift, some context, which gives another aspect of this. And if you trace the proof of Krieger himself, you can already see that it applies to some bigger class of stuff. But something with some kind of synchronization.
Mm-hmm.
So it's not the optimal class, but some restrictions are necessary. Okay, so this answers your question?
Yes.
Okay, so now for the statement of this theorem, so I have now a stronger condition on the target subshift, which I will define in a moment briefly, but not go into details about. Weakly locally extendable. It's a strange name. Of course, it implies there is another property called locally extendable, which I will not define at all. It will not be used in this talk, but it will. It's a new property. It's kind of an ad hoc name that I invented. It's not kind of a well-known property, but it satisfies many things that make it, I think, worth having a name. And X is an arbitrary ZD subshift. Okay, so now no restrictions at all at S, and then I say, when does X embed it to Y? So for example, for simplicity, you can think about, and it's already a new result, and maybe it's the basic interesting case where Y is just the full shift. It's non-trivial in this case. It's kind of, basically you can think about Y equal the full shift, and then you say X is a subshift, is a subsystem of Y, is isomorphic to can embed into Y, if and only if, and I will give necessary and sufficient conditions. The conditions are the following. For every subgroup of ZD, either XL is topologically conjugate to YL, or the entropy corresponding to XL is strictly less than the entropy corresponding to YL. Now let me say what this is. I have to say XL is basically the set of points which are fixed by L. But to make it technically correct, you have to have a distinction between the case where L is a finite index subgroup and an infinite index subgroup. So if X is a finite index subgroup, it's the set of points whose stabilizer is exactly equal to L. Like, for example, let's take D equal 1 and take a subgroup of Z. There are two kinds of subgroup for Z. The trivial subgroup, which is of infinite index, and like NZ for some integer n, which is a finite index subgroup. So for the case of D equal 1, if L is equal to NZ, then this would be just the points of list period n. XL, if L is equal to Z mod to NZ, this would be the points of list period n. And now, okay, this doesn't happen. And if XL is the trivial subgroup, then XL is just X. Okay, so XL, where L is a trivial subgroup is just X. And this is saying, and now what you see, okay, why are these conditions necessary? because an embedding would take XL into YL injectively. And you see that, okay, on XL, I should say, the actions of ZD on XL factors through the quotient group, ZD modulo, right? If you have a point, you look at all points which are fixed by the vertical direction, then, you shift it. It doesn't matter which direction exactly you shift it. It just matters which horizontal coset you shift it by, right? Vertical shifts leave it invariant. Okay, so I want to make sure the statement of the theorem is clear. Okay, there's a part of the statement, questions so far. I will briefly define this property, which I haven't yet. It needs to be defined so that, just the statement is complete. And then I will just remark again and comment why, for the case d equal 1, this is exactly Krieger's theorem. Okay, so okay, the definition that I owe you, weakly locally extendable. It's a you don't have to spend too much time on this, but what it means is the following thing. I mean, I take two finite sets. I think of them as windows, F and W, finite subset of ZD. Sorry, this notation sometimes is used for finite subsets. And what I impose is that if I look at Y star FW, which is like the space of star, I think about is undefined or Joker or something like that. It's the set of patterns with partially defined patterns.
It's the marker, not usually in all the papers there is a star for the marker.
No, so here it's not a marker. It's not a marker. It's like, and it's not for all the papers. This is used in other papers as well. This is like an unknown or Joker or something like that, like the open wildcard.
Okay.
So what it means is like, I take these are configurations where, everywhere that I shift them, I didn't use this notation, it's not consistent. Sigma V means shifting by V. If I shift them by any translate and I restrict to F, then I don't see a forbidden pattern. I mean, if it's defined and it's not defined to be a forbidden pattern. And also I demand that there are not too many stars. So, I mean, if I restrict it to to a big enough window, W, I don't see all undefined. So it's kind of, the undefined places are not too, are not, it's defined in reasonable part of the space, right? The part where it's defined are syndentic, the W syndentic. And where it's defined to be okay. And the condition says that you can take something which is partially defined and complete it to something which is completely defined in such a way, in a continuous and equivariant manner, and in such a way that, if everything was okay, then it stays as it was. So Y is a subset of Y star FW. Okay, so it's a slightly involved definition, but it satisfies many nice properties. It's topological. It's invariant under topological conjugacy. For Z subshifts, it's equivalent to being a mixing Z SFT. Okay, there are many in Z. Many strange properties all degenerate. So it's just coincides for Z SFTs. It coincides with mixing, topological mixing, and one crucial property that it has is that if you have a subshift that satisfies this, and you look at if Y satisfies this, and you look at YL, right, the things that are stabilized under the lattice, they still satisfy this. It's inherited by, restricting to fixed points. That's crucial for this kind of proof. So, I mean, I can elaborate on this later, but for simplicity, you can think about Y being the full shift. There, definitely, if you have a partially defined pattern, you can complete it any way you want. Okay, so now let's a few more words about the conditions. So I have, if L was a finite index subgroup of ZD, then XL, okay, these are the points which are stabilized under a finite index subgroup. Okay, so ZD. So it means, basically it's enough to know them on the, if you see a fundamental domain of the subgroup L, then it determines the whole configuration. So there are only finitely many points in XL, could be 0, but it's a finite number. And XL is a finite discrete set. ZD modulo L is a finite abelian group, finite group, that's what's important. There's no topology here, and the action is free, right? It's because the definition, it was the points that whose stabilizer is exactly L. So the action of ZD modulo L is free. So saying that the two conditions, 1 and 2, which I'll repeat, they just amount to saying that the cardinality of XL is less than or equal to the cardinality of YL. And in the case of Z, the subgroups, okay, as I said, they come in two flavors. There are finite index subgroups and the trivial subgroups. So the conditions 1 and 2 are exactly the conditions in Krieger's theorem. I can go back and review the statement if it's the statements of these theorems to convince you, or
But wait, you are talking about the original.
I'm saying that
the original it was the
I'm saying that these two conditions, right? If D is equal to 1, if L is a finite index subgroup, then saying that 1 or 2 holds means that just that XL, the cardinality of XL is less than or equal to the cardinality of YL. And for finite sets, for action of a finite group on a finite set, topological action, topology is discrete, saying topologically conjugate means that the cardinalities are equal, okay, for free actions. So topologically conjugate in this case just means equal cardinality. And the entropy of a finite group, okay, it's basically up to taking logs and normalization, it's the cardinality. I mean, it's a bijection with the cardinality. So, and then, except for the finite index subgroup, you just have the trivial subgroup, in which case XL is X, and then the condition is just the entropy condition. So it exactly coincides with Krieger's theorem. The case D equal 1 coincides with Krieger's theorem. Okay, now what you have to understand is somehow, if you want to have a condition that embeds all subshifts, including non-free ones, then somehow you have to take care of quotient groups along the way. You're kind of forced to do it because XL must embed into YL. So this is how the proof will proceed somehow. You do it inductively. The induction is, what is inductive? Okay, so for subgroups, you have kind of a partial order of inclusion, but these are abelian subgroups. So I do kind of a double induction. I mean, the external induction is on the rank of the subgroup, like a finitely generated abelian group. It's always isomorphic to some zk times finite abelian group. So the external induction is on the rank, and the internal induction is on the torsion, the size of the torsion. But kind of doing it in steps.
I don't understand. This only takes care of the, let's say, periodic points.
Okay, no. I mean, there's the case of where L is the trivial subgroup. But this is kind of the final step.
Okay.
So, I mean, so let's say, so in essence, the proof says, okay, let's suppose I took care of all the non-trivial L's. Now let's do the trivial L. Okay, but how did I take care of the non-trivial ones? Exactly the same manner somehow. Okay, so and now I will discuss this matter. Okay, so this is the nature of the proof, the strategy. And what you get, once you realize that you kind of, this is how to do it, then one thing you automatically get is that somehow I was interested in ZD, but you have to deal with finitely generated abelian groups that have torsion. So you get all finitely generated abelian groups, And somehow there's an easy general argument that says that you know, if you know it for finitely generated groups of some class, then you know it for the countable ones as well. There's a soft argument for the non-finitely kind of. So you automatically get it for all countable abelian groups. It's not a big step, it's not a big deal, but it does not require more effort. And there is another thing you get for free from this nature, which is already new for Z. For the case of Z, it extends Krieger's theorem. And now let me say the slightly more general formulation of the theorem. And it's not a generalization or something. This is really what you're proving. This is the proof proceeds by all of this. So it's a kind of it's more general in the sense that the group over which I'm doing it is a countable abelian, and I explained that this is not a big deal. And the other thing is that there's something relative. I mean, I'm extending something to start with. So I start with the closed gamma invariant subset x0 in the source subshift, and I'm already given an embedding of x hat in Y. Okay, so I am given kind of a bootstrap initial step, and you know, and then I say that I can extend it to an embedding if and only if for every subgroup gamma, okay, there's necessary condition to embed it. So either, okay, condition one is somehow vacuous. It says either I know it extends to an isomorph, so the restriction of x hat to x hat L, the L fixed points, extends to an isomorphism of the L fixed points, or the entropy is directly listed. So if I take x hat to be the empty set, this reduces to the previous statement. Like a function from the empty set is nothing, right? It's
but I wonder, shouldn't there also, but because here you assumed injectivity, so this is the context of embedding. But when we talk about relative Krieger, we may also imagine some theorem that tells us about factors.
Right, absolutely, you're absolutely right. And by the way, the theorem that Sophie McDonald proved, it somehow involves factors. It tells you how to do embedding through factors in some sense, but in the context of Z. Okay, but I mean, it's different direction. So completely true that you know, there are ways to imagine other forms of relative, but this is.
But wait, is there such a theorem? Did Krieger prove such a theorem?
No. This is newer. Both this version and the other versions are completely.
No. I'm asking about you have some conditions on entropy. You have conditions on periodic points, and then you want to say that there is a factor.
What is the setup? You're saying, suppose I have you know, some factor of x and some factor of y, factor of x embedded into factor of y.
No. I have x and y, and I'm asking the question if there is a map from x onto y, the equivalent map.
Ah, from x onto y. Okay. When does x factor onto? Okay, this is Mike Boyle's lower entropy theorem. Lower entropy factor that I refer to. Lower entropy factor theorem. Yes, this gives necessary and sufficient conditions for one mixing subshift of finite type to be a factor of another.
Okay.
Yes, but so it's similar in flavor in terms of the proof, and in terms that the conditions involve periodic points and entropy. Okay, the conditions of periodic points are different because if we're factoring, you can have something of period 6, you know, mapping onto something of period 3. So
right.
It's not exactly the same condition, but yes.
Because I think naturally this would be referred to as relative Krieger.
No, this is it's not a theorem about embedding, it's a theorem about factoring. So it's not really. Right. What I mean here is that, you know, not only do you do an embedding, but you started, you know, you're giving some base and you must extend upon that.
Right.
Okay, so I don't know. Maybe there's another name other than relative. I don't know, increment. I don't know. But anyway, this is the result, and so this clearly implies the previous theorem, and somehow the inductive nature of the proof, suggests to proceed by doing this. And this formulation, okay, it's a little bit new already for Z. It's not a big deal. I don't think it's been formulated. Okay, so now I will explain kind of the rest of this talk, which I will explain, whatever I can about the proof, steps of the proof, and go into details as far as the time and the audience permits me. Okay. So I will first outline the steps. So the first step is to find a special pattern in Y, the target subshift, which will be used, right? It's not the star that was in the Y star. It's an admissible pattern. It will be used to mark something, or to stamp something, tell you you're in a designated location. And the pattern, what does it need to satisfy? So first of all, it needs to satisfy the thing that it's designed to designate something particular. So you need to be able to do without it somehow, to code information without it. So if I let Y tilde be the subshift of Y, or the set of points in Y where the pattern A never occurs, in any translate of it, if you take a pattern, Y tilde is the set of points in Y, so that any translate of it restricted to the set P is not equal to A. And I want the pattern to be such that if I forbid this pattern, I still have satisfied the necessary conditions to embed X. So I still have enough entropy, the entropy is still bigger than the entropy of X, and still have, also for the non-fixed points, for every L, the entropy of Y tilde L is bigger than the entropy of XL. And of course, to do this, there were two cases, either conjugacy or strict inequality of entropy. The conjugacy case, I'm done. If I already know that, I can extend, then, there's nothing to do. If there is conjugacy at the level of L equal to trivial subgroup, then I'm done. I know there's a conjugacy is an embedding, the resistant. Otherwise, okay, so this condition will tell me I have a little slack. I can get rid of something. And now there's something more from the pattern I need. I need somehow that the pattern does not have substantial self-overlaps. Okay, it's a technical thing. I don't know how much I will be able to explain how it's done in general in this while, but for illustration, if you take Y to be the full shift over, let's say, two symbols, which is an interesting enough case, which maybe we should keep in mind, then this pattern A could be something like, having 1 at 0 and V and 0, everywhere else in some big board. Okay, so I'm taking a pattern which is, it has 1 and surrounded by zeros. This could be something like that, roughly. And then I claim that if I take the full shift and I forbid 1 and many zeros around it, it does not decrease the entropy by very much. And if there are many zeros, then also it doesn't hurt the periodic point with the X, Y, L for L containing some small vector. And additionally, we actually need slightly more. Okay, remember there was this row hat. We had in this formulation a partial embedding. So I need this pattern that I choose not to interfere with what was already given to me. So I need it not to occur in the image of the partial embedding that I have, or the embedding of the partial subset. And this is possible unless this partial embedding covers everything, and then again, I'm in this case. If XL is, if this is surjective as well, then and the conditions are satisfied, it means that X hat must be X already. So I must have something here if I'm not in this case, and it's possible. Okay, so this is the first stage. They choose this marker stamp. It lives in Y. Then the second substantial step, which I have to elaborate on a little bit, and this is the following. I look at this X, this row hat, okay, this partial embedding that I'm given, which could be empty, but suppose it's not, it will be important later. Well, what does it mean to have a continuous map? Here it's injective also, but what is a continuous map? Continuous in this topology just means it depends on finitely the output at a given V. It just depends on finitely many coordinates, and the equivariance means it depends in the same manner. So there's a finite set W, like a window, and a function from W to the V, from W patterns to A, such that row hat of X at V is just applying this capital phi to X shifted by V, restricting it to W. This is what's called the sliding block code. It's telling you what is the structure of continuous equivariant maps between subshifts. They're given in terms of finite data. Now, right, so what did I say? Now, okay, that's the point that I was saying. Using the induction hypothesis, okay, so I'll explain this. I am assuming I can do the theorem for smaller gammas, smaller in the sense that I'm restricting to finitely generated. So smaller in the sense of rank and size of torsion. So in this sense, if I restrict to X hat to XL and YL, I can do it for L, which is non-trivial, finite, subgroup gamma. I can extend. So I have the partial. So the partial embedding of X hat. That's another thing. I can assume X hat already contains, a finite number of XLs.
Mm-hmm.
Like, okay, let's go back to let's go back and explain how this idea manifests in the proof of Krieger's theorem in Z. What it means is, okay, I have Z, and I can do it for groups which are small, for quotients which are smaller than that. What's smaller? What are quotients of Z? Just finite cyclic group. For finite cyclic groups, I can do the embedding. There's nothing, by induction, it's trivial. It's just choosing a bijection of orbits. I want to look at, I'm assuming that I want to prove that, if I have a finite cyclic group and a subshift over a finite cyclic group, and it satisfies the entropy condition, means that there are less points in XL than YL, and I can embed. What is embed? There's no topology. It's just an injection, an equivariant injection.
But in this example, where does the torsion come in? I don't understand the torsion.
So the torsion, so for example, so let's the torsion comes in because so in Z, right, of course, any quotient of Z, which is by a non-trivial subgroup, is a torsion, right?
So it's torsion in the image but
yes,
in the
no. The torsion, the induction is on the rank and the size of the torsion of ZD of gamma model.
Right.
Not over, right? L's are torsion free, might be. So that's what I do. So this is kind of taking care of the periodic points, and somehow the idea is part of the idea. This for full shift or for subshift more generally that satisfy this strange condition of a weak local extendability. If you have strict inequality of entropy between X and Y, then there can only be then there's a finite number of elements of the group, such that any L that does not contain any any non-identity element in this finite set, XL will also satisfy a strict inequality automatically. So it generalizes the fact that if you have a subshift, if you have a subshift which has you have a subshift, a mixing Z subshift of finite type, and you have another subshift that's Y, and you have X, which is strictly smaller entropy, then from some period onwards, the number of periodic points in X will be strictly less than the number of periodic points in Y. You cannot have equality for infinitely many, otherwise you will have equality in entropy. And there's a multidimensional generalization, or actually generalization for general amenable groups. It follows basically from this key lemma about entropy, written correctly, of course, with the correct equality. Okay, so all right, step 2. So this kind of takes care of points with small periodicity. Now the next step, this is the key step. So the next step is to construct continuous equivariant function. I will define it from X. This is the source subshift, which I don't assume anything about except for the entropy condition. So it can be strange. It's not a subshift of that.
So it's equivariant, not equivalent.
Sorry. This is a typo. Yeah. Continuous equivariant function. This is probably a spelling autocorrect error. An equivariant function from X to the space of partial tiling. What do I mean by partial tilings? I will, impose further conditions, but I just mean pairwise disjoint subsets of gamma, which are each of which is K delta invariant. Now there's a topology in this space. The topology is basically, you take, it's a set of, it's a collection of subsets of gamma, which are pairwise disjoint. You just look at the ones that intersect some big window, and this is a neighborhood, right? It's like this space is it's a totally disconnected Polish space, but if I have a continuous equivariant function, the image is just to a compact subset. So actually, there will be only finitely many shapes that will appear. And so there are finitely many shapes up to translation. I mean, you actually partially tile by, a finite number of shapes and they translate. And for each shape, for each of the finitely many shapes, they're K delta invariant, and I choose the K big enough and the delta small enough so that by this basic lemma, I have an injection from the X admissible patterns of shape S plus W, slightly extended, to the S patterns that are Y admissible. There are more in Y than in X, even if I slightly extend X. This is how I choose the K and the delta. So the strict entropy inequality tells me that if S, for any, depending on the entropy gap between X and Y, there exists a K and a delta. Okay, for every W finite set W tilde, there exists a K and a delta, such that cardinality of this is strictly smaller than the cardinality of this for any S which is K delta invariant.
What is cell? I'm sorry, I'm confused. There is shape and there is cell.
There is shape.
Yes.
Right. So I mean, the word cell here, you don't have to. I mean, it's just for context. Formally, it doesn't play any role. Right? For every S, for every subset, for every S, the cells. Okay, I'll just explain the terminology. The tiling is by K delta invariant subsets. Okay, so I take some subsets with a disjoint. I call them cells.
Okay.
We think about them as cells. This is just a name. So for every S, which is K delta invariant, I choose such a function. I mean, the K and the delta were chosen by the entropy inequality and the basic lemma about entropy, so that there is an inequality of cardinalities here for every S, which is K delta invariant. Because, you know, the cardinality of this, if I divide it by the size of this, take log and divide by the size of this, it's bounded above by the entropy of X. And if K delta, sorry, it's bounded above by the entropy of X. Sorry, the other way around. This is bounded below by, if I take this and I take log and divide by S, it's bounded below by topological entropy of Y. If I take S to be sufficiently invariant, then this is bounded above by the topological entropy of X plus epsilon. I take epsilon to be smaller than the entropy gap. Then I can choose such an injective function. So I choose the injective function. And now I sort of can say, you know, if I have this equivariant function and I have this choice of cells and I have the induction hypothesis, then I can more or less complete. The way I do it is I do the following things. So I have a configuration in X, I do the partial tiling. Whenever I have a cell, like a shape that covers something, I apply the corresponding function, and this is the pattern I put in Y. Now, the pattern in Y, it's supposed to encode corresponding pattern in X, slightly enlarged. This is what this phi says. Oh, this is the mistake. This phi should be psi. Phi should be psi. So the embedding rho would say that rho X restricted to S would be psi of S of X restricted to S plus W tilde. So knowing the pattern of X restricted to S encodes what was in X in a slightly bigger set, slightly extended.
Could you please repeat again what is W tilde?
W tilde, okay, I didn't say the quantifiers, but I mean, it says the claim is that, you know, for every W tilde, there exists a K and a delta, so that I can do this. And I choose W tilde, you know, to satisfy something. I will say in a moment. It will be slightly extended, you know, so that something works. I will say it will somehow. I will say it in a moment. I will say how it's chosen according to something. Okay, it's there's actually a slight elaboration of that, but it's chosen according to some parameters of Y. Okay, and to some properties of Y. And whenever whenever, you know, I have a part of the configuration which is not inside the cell, okay, it's a partial tiling, that not everything is covered, something that's not covered, then, okay, I'm saying that the equivariant, this partial tiling will satisfy the property, it will be constructed so that the parts which are not covered by tiles, if I take a pattern of X and restrict it to big W, and W was it will be slightly bigger. W was kind of what I need to see to apply the partial embedding that I already have, which was extended to contain the periodic points. Oh. So if I restrict X to W, then it looks like the part that I already know how to embed. Okay, in the case of Z and Krieger's theorem, it means that the parts that I'm not covering by cells look periodic with a small periodicity. And then, in that case, I can, it looks like something here, something in X hat, and rho hat was can be applied to it. In some sense, this capital phi, it works whenever I have an admissible pattern in BW. So it's a place where I can embed using the induction. I will say in a moment what will be W tilde. Actually, I need some more because there's also the inverse of rho hat. Rho hat is injective. There's an inverse of the image. It also is given by some sliding block code. So I need to be slightly bigger to account for that. And furthermore, okay, so there's another thing I require from this part. I require that this injection, these shapes S, they all contain the shape P, which was the support of this marker stem. And in some specified location, and only that specified location, I see the stem. So I know sort of where the centers of the cells are by looking at the coding of the cells. This is what this condition will mean. Maybe I will illustrate it in a moment. So that's the strategy. Okay, you see, I take my group ZD, I equivariantly, I put cells inside it that cover everything that I didn't know by induction how to embed, sort of. And for each shape, I use the entropy gap assumption to kind of have an embedding. And I also code sort of the centers of the cells. So now if I see the image, I know where the cells are. This is what will happen. And then I can decode sort of. I know where the cells are. For each cell, I can do this is injective, it decodes, and outside I do the decoding by the inverse of rho outside the cells. Now, okay, now the content and everything is how to do this, right? This is there are other complications, but the essential part is how do I do this? How can this be done? And the idea of this, okay, it consists of two ideas, both of which appear to some extent in Lightwood's work, but there's an additional ingredient in both of them. So what you need is to choose the center somehow, and this is by a version of Krieger's marker lemma, which I will state in a moment. And then once we have the centers, you have some points in ZD or in some Gurion group, you can take the Voronoi diagram. For each point, you take the set of points which are closest to it. Now, this works if your points are what's called a Delaunay set. The distances are bounded, but also they're seen that they're bounded below and bounded above. They're not too close, they're sufficiently separated, but sufficiently dense. Here, I cannot guarantee that they're sufficiently dense. I can have points which are, in this part where I already dealt with before, and there I don't have points. So it can be arbitrarily big areas without the points. Therefore, I can't take the Voronoi diagram. I need to take a truncation Voronoi diagram. And I will say about, and this is what I will, finish off by saying.
Right, explaining what you mean by truncated, right?
I will say it will be in a couple of slides. I will explain.
All right, okay.
I will explain. But let me just add another point, which maybe I don't want to invest too much time on. This sketch of these three steps up to details, okay, which are non-trivial, but will be there. It finishes the proof for the case, let's say, of the full sheet. Now, it does not explain why I needed this weak local extendability property, how it plays a role. And this is step 4. So the idea is, I took the pattern in X and I encoded it into a slightly smaller pattern in Y. And the reason is that I use the extension property to fill in the little boundary gaps. These will be used. So I think about them as undefined and put stars, it puts the extra joker symbol, in the places which are near the boundary of the cells. And then I extend them using this equivariant function. This is exactly what happens. Okay, so that's the 4th step. This is where it's done. So and somehow this 4th step, which is easy using this assumption, is a part that like Lightwood really struggles with to do under, slightly stronger assumptions, slightly weaker, assumptions on the subject. So his kind of square mixing condition is slightly weaker. It's a slightly stronger result for the restricted case of the aperiodic. And it's a real struggle for him to do it. That's why he needs 2 papers. The second paper somehow weakens this condition a little more, just in the case of d equal 2. There's something just 2-dimensional. So I'm not dealing with this final part at all. But here it's kind of an easy step. Yeah. So somehow, okay. So now my plan is to extend sort of on the proof, but mostly kind of on this 3rd step, which is somehow key step. So there are 2 parts. First of all, there's the part of getting the points. And I will say how it's done. So this is in terms of a very general lemma, which I will state now. Now, Krieger in his original paper had a marker lemma. It was stated for the case where the acting group is Z. And another sort of restriction, but the sort of similar proof applies. And in Lightwood's paper, there's a statement in ZD and the same proof sort of, and but it somehow avoids it's stated for 3 actions. And there's another statement of this theorem in a paper of Jonathan Gutman and Elon Lindenstrauss and Masaki Tsukamoto again. And there are many versions of this lemma. And the proof is always essentially the same, but the statements vary from one paper to another. So it's not really new, but nevertheless, I will give the formulation. So formulation is quite general, and not the first time you can. You have some countable group acting on a totally disconnected space, and this could also be generalized in various forms, but not exactly. And you have some finite symmetric set F, which contains the identity, or you cannot contain this, then you modify the statement accordingly. And you have a closed subset of X, which is sort of the good points. So what does it need to say? For every X in V and G, which is in F, but not the identity, for any non-identity element of F, it does not fix X. So points in V are not fixed by points in F except the identity. And now I give you D, which is a Klopen set, which is disjoint from V. Then what I claimed is that there exists, okay, we'll need to say it. So then there exists a set C, which is a Klopen, and it's an F marker. What does it mean that it's an F marker? It means that translates of C by elements of F, except the identity, are disjoint from C. So on one hand, translates of And on the other hand, if I take all the translates of C in F, they cover V. Okay, and C is disjoint from this D. So now let's see what this does, this lemma does. So let's what does it say in the case of subshift? So let's take X to be, you know, a subshift, and let's take F to be a small like set of points containing the identity and some smaller points. Okay, and let's make it let's symmetrize it. Then, you know, it says that if I take V to be a set of patterns, you know, I take a sufficiently large, you know, ball in gamma or whatever, and let's take not V, sorry, I take a sufficiently large ball in gamma, and I take all the you know, B, all the B patterns which do not look as if they are periodic with some fixed with some element of F. Okay, which already by looking at this pattern, I know that it cannot have F periodicity. I look at these patterns, and I let D be the other patterns, the patterns which, you know, possibly allow for periodicity of F. So D intersect F would be the empty set, and actually V, so that V union D will be X. It's a partition of it. Sorry. Yes. So then what it's saying is that I have a Klopen set that, you know, I have this Klopen set, and the idea of this Klopen set is that, you know, I take every point and I look at where one of these patterns from C occurs, where the C, you know, where the Klopen set C occurs. So first of all, it doesn't appear too closely. It doesn't, if there's occurrence of it somewhere else, there will not be occurrences in F, except the identity. Right? So they're separated. And on the other hand, for every location of gamma, somewhere within F, I have an occurrence of the marker, unless it looks like it's already periodic with period in F. Look, you know, you look at it in this big window, it looks like it's periodic. This is what the Klopen marker lemma says. It has a relatively short proof, which is essentially the proof in Krieger's case, where gamma is Z and F the symmetric interval. Okay, so I'm nearly out of time, I think. Now, once I have this, so I have a subset of points in gamma, I can look at the Voronoi cells, they are truncated Voronoi cells. So I have C, it's a subset of gamma. Gamma here, let's say you can think about it as ZD, or some group with a distance. Let's say with a translation in left invariant distance, or, you know, let's say commutative group and invariant distance, like the Euclidean distance, could be in a second. And the Voronoi cell of V0 in C with respect to C is a subset of gamma. Let's say think about gamma as being ZD. It's all the points V. So, wait, something is wrong here. Okay, V0 here should be W. Sorry, that's the typo. So the Voronoi cell of W is all the points V such that the distance of V from W is smaller or equal to both R and the distance between any other point.
Okay.
Okay. And now this is not a partition, at least there's ties, so you break ties somehow. You make some rules to break ties, it's not so important. I mean, it's cool, they're equidistant points, you know, make up some rule to break ties. Let's do some perturbation.
But wait, if you are introducing the R,
Yes.
there will be points maybe that.
So, okay, so this is not a partition. This is a partial.
Exactly.
It's not a tiling, it's a partial tiling. Exactly. There are points outside everything.
Exactly.
That's the main point. Now the point, right? So let's have var C, and I forgot the index R. Denote the R truncated Voronoi diagram of C. The collection of R truncated Voronoi cell should be a C. Okay, and I'm saying this is a partial tiling up to the fact that there's some overlaps on the boundaries. Let's forget them. Let's imagine that I solve this problem of overlaps on the boundary by breaking ties somehow. Now the point is that for the function C from C to Voronoi RC is continuous and equivariant from any, it doesn't, you have to look at the finite distance. You just need to look at the finite distance of 2 hours or something like that. With respect, so I didn't say what the topology, I kind of illustrated what the topology on the partial tilings are, what it is. Basically, what it means is to determine the Voronoi cell, you only need to see a finite distance 2 hours. And it's equivariant, assuming that the distance is invariant, right? Like the Euclidean distance. So, right. And then here comes an argument where we do use the ZD, it's a Euclidean group, and we use Euclidean geometry. This is how it goes. When the distance is Euclidean, the truncated Voronoi cells are convex cells. And convex cells that contain a big ball, they have small boundary. This is geometric fact, basically. And so if R is sufficiently big, and the sets in C, they're sufficiently separated, are separated, then the cells are will be K delta invariant. And now here is a crucial point, and it's important, but I will not be able to stress it to elaborate on it too much. There are two kinds of smallness of the boundaries that I need that are different. There are boundaries between cells that are adjacent. And there are also places where you have a cell and it's adjacent to part which is not type, it's outside cells. Now, by increasing R, the truncation, I can make this part of the boundary that's near the not cell, not between cells, but between a cell and a not cell, as small as I want, without changing little r. And this is crucial for the way we choose the order of things, because we first choose the marker stamp somehow in terms of the entropy gap. Then we choose the little r in terms of the separation. We choose the k and the delta in terms of the entropy gap between the subshifts. This tells me this tells me r. This tells me which in turn tells me kind of what small periods I need to deal with separately. And then I extend by induction the embedding to these points. And now I have a partial embedding. Now this partial embedding, it has a window. The window depends on, the small periodic points that I already chose and the small r and whatever. I cannot fix this. But now I have the freedom to choose big R. And this depends, the freedom of that is reflected somehow in the choice of this B and the C, okay, this big ball B, of how close to periodicity, to the known part I need to be in order not to be covered by a cell. So this part is important. It's important to have the flexibility to separate this little r. Now, okay, so here's something empty that I will just finish off.
Okay.
Kind of sketch why this is injective. So to see that it's injective, you just, you first recover the markers from the occurrences of this marker stamps, this special pattern A. You reconstruct the truncated Voronoi diagram from this. You know the cells. For each cell, you decode what is in it. And then you use the outside you decode by applying the inverse of the, partial embedding that you're given, which includes the inductive part. That's it. So
okay. So first of all, let's thank the speaker. I found the talk very interesting. Are there any questions?
okay.
Um,
Okay, so thank you.
no, I do have a question.
Okay, no, yeah, we can. I'll be happy to discuss later. It's fine, but
Well, first, let me make a comment about markers, because markers in mean dimension theory. In the Lindenstrauss paper in 1999, he actually uses markers, but he doesn't call it markers. And in 2015, I introduced the name marker in the context of non-zero dimensional
right,
systems.
yes, that's true.
Before that, it was only, I think, in let's say symbolic, maybe zero dimension.
Right. Yes,
And in the moment that this was introduced, then suddenly you could discuss it, and there are, since then there have been non-trivial progress. For example, that you can show that aperiodic finite dimensional always has markers in the Z, and recently it was shown that that aperiodicity is not equivalent to marker property in this context and so on. Okay, my question is, and it's a big question, but just to, I understand this works for under the abelian assumptions for gamma.
So the markers are not, so
I'm talking about your theorem.
The theorem is abelian, yeah, the 4 abelian, yes.
So there is some difficulty to extend this to gamma non-abelian.
I'm sorry, what was the question?
There is a difficulty of extending your.
Yes, there are some. I mean, I have thought about it a little. I think there are substantial difficulties of various forms. Okay, so maybe I'll just say 2 words or something about what. So one kind of inherent difficulty in extending this kind of theorem, if you're also allowing, non-free action, is the fact that gamma mod L need not be normal. There's some stabilizer need not be a normal subgroup. So there's some difficulties involved in that. It involves things like this notion of invariant random sub. Okay, it's not known completely, but there's an inherent difficulty. Like gamma mod L is not a group. It does not act on something, and you have to make sense of it. The other difficulty, which is also substantial, even if you're kind of restricting to free actions, which is already interesting and very challenging, then the difficulty comes from the fact that to make this partial tiling by almost invariant subsets, this used the convexity, like Euclidean geometry argument. Specifically, right?
That's actually interesting because you mentioned it for ZD, but you claim the theorem.
Right. So yes, that's true. So right. So the point is, this is kind of a rough, coarse geometry property, large-scale geometry property. So it works the same way for things that are like virtually ZD. Right? So it's not so it's more than abelian. This is not the most general setting, but so let's put it this way: finitely generated abelian groups, which are large, coarsely look like ZD. They coarsely look like ZD.
Right.
Not a problem. But if you go beyond that, then completely different arguments are needed. Probably. For this part, I mean, a lot of the ingredients work, but this particular part needs something more.
Okay. So are there any other questions? If not, let's thank Tom again.
Okay, thank you.
Thank you.
Let me say that next week we don't have seminar because it is between holidays. So the next seminar is in 2 weeks.